Alrighty, welcome back to 353 and good morning. Wow, it's early. All right, so next topic, IPC or inter-process communication. Now we know that processes are independent. We need some way for them to actually communicate with each other through IPC and through the kernel. Otherwise, well, if a program does not communicate with anything, it is worthless. So again, as a reminder, IPC, or inter-process communication, is transferring bytes between two or more processes. So reading and writing files technically is a form of IPC. The processes do not need to be alive at the same time. So one process can write to a file, it can end, another one can come along, read that file. Technically, that's inter-process communication. The read and write system calls just allow any sequence of bytes. So they don't really care. As long as you write bytes, they are happy. So we will just dive into our first code example. So a simple process could just read or write everything it reads from the standard file descriptors. So here is my little program that is deceptively simple, but we'll see that it's actually useful. So we have a main. I declare a character array of 4,096 characters. We'll see why I use this number once we get to virtual memory. It's a special number other than it being a power of 2, so that's 2 to the power of 12, but we'll figure out later why that is useful. But that's just some space set aside that when I do a read system call, all the bytes are going to be written into that array. So next I declare a variable called bytes read. That's s size t, so that's sign size type. That's what the type the read system call returns. So the read system call, or sorry, the read C wrapper of the system call does what all the wrappers do, not the cool kind of wrappers. It will return -1 if there's an error. Otherwise, it returns the number of bytes read from this file descriptor. So file descriptor 0, that's just defined by convention to be standard input, which most of the time when we run our application is connected to our terminal. And then I have to give it an address to write to, so I give it that buffer and say the number of bytes it can write is up to the size of the buffer. And I'll just put it, and then I set it equal to bytes read, and that assignment will return the number of bytes read. And I keep doing this loop while I read greater than 0 bytes. So there's still some input I'm reading from the file, or whatever, or the terminal, or whatever it represents. So I'll keep on doing the body of this loop as long as there's some data. Then the next thing I do is I write. So I write to file descriptor 1, which is standard output, and I give it that buffer as well. So I give it that buffer that it was just filled from reading, and I am writing it back out to standard out. And I only write the number of bytes I have actually read in. And then the rest of the code is error checking. So I check if bytes written is equal to -1, in which case there's an error, so I'll just print out some error information. And then technically I should check that the number of bytes written is equal to the number of bytes read, kind of like checking if printf was successful, but we don't do that. But here I'm going to do that. I will write an assert statement. I don't actually check it. What I like to do is program defensively, so any kind of assertions I make or anything I believe to be true, I will write an assert statement. So if I'm wrong, instead of something weird happening, it will just fail at that point and tell me why it has failed. So I'll assert that the number of bytes read is equal to the number of bytes written. And then aside from that, if I break out of this while loop, read either returns 0 or -1. If it returns -1, that means there's an error. Otherwise, it should return 0, and 0 signifies end of file. There's no actual end of file character. If anyone has told you that before, it's a lie, or it's only true for whatever library they're using. Kind of like with C strings. Strings don't have to end with a null byte. That's something C made up and they kind of regretted it. Same with the end of file character. That's something someone else made up to signify end of file instead of just having the number of bytes of the file. So anyone have any problems with this program? Just reads from file descriptor 0, standard in, writes to file descriptor 1, standard out. Looks kind of useless, right? So let's run this. So if I run it, it just hangs here, right? Nothing happens. So if I want it to do something, what should I do? Probably type in my terminal, right? So what if I wrote hello and then hit enter? Well, oops, I hit hello I. Well, if I do hello I and hit enter, as soon as I hit enter, well, that's me sending information from technically my shell to that process. Then that process read that information, so hello I and a new line character, and then it immediately wrote it back out to standard out. So it kind of like echoed it back to me, not really the echo command. Does this command look familiar to anyone, how it behaves? Any command you might have used before that does this exact same thing? No guesses? Yeah?
String copy.
String copy? Like the command I write in my shell, not the C command. No one's used a program like this before? Has anyone ever used the program cat? This is cat. So this is exactly what cat does if you don't give it any arguments. So it's actually more useful than you think. If you accidentally type cat, how do you get out of it? Sorry? Control C. Control C is one answer. Do you know what Control C does? Close the terminal? Not quite. Anyone know what Control C does? Yeah? Kills the process. Technically not. Any other guesses? No one knows what happens when I hit Control C? Sends a signal to that process. Yes. What sends a signal to it?
Shell.
Yeah, so the shell would send a signal to the process. Anyone know the proper way to exit cat without sending a signal to it? Probably not. So how Unix anything signifies end of file is if read returns 0, which means no more input is available. If I want to exit cat or tell my terminal that I am done typing to it, I can actually hit Control D. If I hit Control D, that means I'm done writing to it. And in this process, when it's running, read will return 0 and then signify that I'm done. So it will break out of this while loop and then finally exit my process. So this is exactly what cat does. If I do cat hello, same thing, it echoes it back to me. Hi, Control D, and then it's done. So by the end of today, we will also see what happens, other ways to exit, and see what Control C actually does if some of you didn't get it before. But any questions about this program? Seems perfectly cromulent, right? Perfectly good program. It's cat. We use cat all the time. It's fairly useful. Most of you probably use cat to like cat a file, right? So we can modify it. And because we are using the standard file descriptors, it's actually a very simple modification. So without changing the rest of my program, I will add some more information to main so I can get command line arguments from it. I will expect the user to type 2, so the name of the program, which gets set by the shell, and then a path to a file, which I'm going to output. So if I don't get exactly 2 arguments, I'll return from main with this inval, so that's supposed to mean invalid input. And then I will check if argc is exactly equal to 2, so someone has specified the file name argument, what I'm going to do is, well, what I'm allowed to do is I can just replace file descriptor 0 with something else. So standard, the process by convention has file descriptor 0, 1, and 2 open. So what I can do is I can close file descriptor 0. So say whatever the original standard in was or whatever it was pointing to, I don't care anymore. I'm not going to use it, so I close it. So now file descriptor 0 is free for my program. And the way Linux and all Unixes assign file descriptors is it will always use the lowest number available. So when I do this open system call of this file, and I'll just give it a read-only flag, the file descriptor I get back is going to be 0. So now 0, which is by convention means standard input, is now essentially pointing to that file instead of whatever it originally was, which was the terminal. I'll, of course, check for errors, and then the rest of my program is exactly the same as before. I don't actually have to change it whatsoever because I'm just using the standard file descriptors, or I'm just reading from file descriptor 0 all the time. So if I run this now, I can even be meta about it. I can, essentially, this is like catting its own file, its own source file. So if I do that, I see the contents of that file without changing anything, right? Just to show you that I indeed wrote cat. So any questions about that fun thing? Kind of useful. Everyone's used this before. This is exactly what cat does. This is basically the implementation of cat, except that the real cat lets you, specify multiple files and it just reads them in a row. But other than that, it does the exact same thing. So questions about that this nice, bright, and early time in the morning? OK, well, turns out if I know how to use my shell, because everything uses the standard file descriptors, I didn't even have to write this open at all. Whoops. I didn't have to write this open to have my program deal with files. As long as I use the standard file descriptors and I know how to use my shell, I can do some more interesting things. So your shell will let you redirect the standard file descriptors. So instead of what I did before with running my open example with the name of a file, I could instead just run open example and then use this arrow thing. So this arrow thing, what it will do is before that process starts running, your shell will in fact replace standard file descriptor 0 with this file to point to this file instead of the terminal. So I didn't even have to do that. I didn't even have to do an open system call in my program if I didn't want to. So just to show that I didn't have to do that, I can run my read-write example, and then I can give it that C file again. So this was my read-write example that didn't have any open system call or anything in it. But using the shell redirection, I can give it, make the standard input file descriptor point to openexample.c. So now I can run it and get the exact same thing. So using the as long as your program uses the standard file descriptors, it can handle files without you actually having to explicitly, write file handling in your program. Cool. So any questions about that? Neat, huh? All right. So another thing we could do is we can actually redirect across multiple processes. So I can use this bar character to kind of connect the standard output of one process to the standard input of another process to make them essentially talk to each other. So I'll just cheat and use cat. So what this will do is take whatever this process writes to standard output, and instead of standard output by default going to your terminal, it's instead going to go to the process on the right of the bar. So anything from standard out on the left is going to go to standard in on the right. So it's going to read it, and in this case, the output is going to be the exact same thing, because this process is writing to its standard output the contents of that file from reading it and writing it out. And then cat, from its standard input, is going to read the standard out of this process, which will be the contents of the file again, and then write out the contents of the file. So in a more roundabout way, I can see the contents of the file again. And since cat behaves like this, I could add a whole bunch of cats if I wanted to. I could be a crazy cat lady, I guess, or man, and do it as many times as I want. I'm just doing it more inefficiently by just throwing more processes at it. So, any questions about that fun thing? Yeah?
Could you re-explain what like the left arrow angle bracket thing is for again?
So the left arrow, kind of, how I like to think about it is it's going to change standard input to point to that instead. So the contents of this file are going to go into this process as standard input. So by default, standard input would be like your terminal, right? So I type on my terminal and then it just goes to that process, like when I typed hello and it spit it back out at me. If I do the arrow, it's like, okay, I do not want the terminal to be standard input. I want the file to be input instead. So the arrow, since it points at the process, is like, kind of, you're feeding that file into that process. And there's also the other arrow, which is if I don't want to see the result in my terminal, I can use the right arrow, and instead of going to my terminal in standard out will go to that file instead. So I can actually use this as a kind of scuffed way to make a copy of a file. So if I called it copy.c and ran it, I don't see anything in my terminal, or it's not asking me to type anything, because when I run this process, standard input is replaced by pointing to openexample.c, and standard output is replaced by pointing to copy.c. So all the output is actually going to this file instead. So now if I look at copy.c, I can see it's actually a copy of that file. So it turns out you don't even need the copy command. You can just use cat creatively if you really want to. So, yeah?
So before, when you ran the command without the left angle bracket, you were able to like type in that from
Yeah.
the standard input being.
Yeah, so if I just run it without any arguments, then since I'm using a shell, the default thing is that standard input and standard output go to the terminal. So when I type something and hit hello, like, and hit enter, then whenever I type that, that goes to standard into that process, and whatever it outputs, so this is me inputting something, and this is it outputting something. So they're both, by default, go to the terminal. All right, any other questions about that? Kind of cool. We can actually copy. We don't need a CP command. We can just use cat in creative ways if we really want to. So that was it. That was pipes. All right, so now we can talk about what happens when we hit Control-C. So, like someone pointed out, if I want to exit this process, people have told you just hit Control-C. If I hit Control-C, some wonderful things happen. It gets a bit unhappy. There's this, in my shell at least, there's this red thing that says sig_int. What the hell is that? So, how that works is technically when you hit Control-C, you send an interrupt. Everyone loves interrupts, right? So you send an interrupt to that process, and the kernel technically starts running it in your process, and that interrupt has an associated number with it. So the kernel sends a number to your program indicating the type of the signal. You can look up the numbers. We'll go over a few today. And your program by default has a few default signal handlers. The default ones will either ignore the signal and do nothing, or terminate your process by calling exit. So Control-C sends sig_int, which is supposed to represent an interrupt from a keyboard, and the default signal handler for sig_int is the one that terminates, and the default handler that terminates will exit with the exit code 128 plus the signal number. So turns out that in this terminal, translates that number back to sig int. But if I didn't have this displayed, I would see that my process exited, if I waited on it or something like that, I would see it exited with the exit status of 130. So knowing that this is the convention, knowing that this is the convention, that it's 128 plus the signal number, if it exits 130, that means sig int is number 2. You don't have to remember the number 2. So you can actually set your own signal handlers with a system call called sig_action, which sounds kind of fun, funner than it actually is. All you do is declare a function that doesn't return a value and has an int argument, and that int will be set to the number for the signal handler. So the numbers more or less are non-standard, but from Linux x86 64-bit, which is what most of you will probably interact with, these are some of the default numbers. So 2 is sig init, interrupt from keyboard. 9 is sig kill, which is terminate immediately. And then 11 is something we've probably all seen before, seg v, or memory access violation, or seg fault, or I screwed up memory, or I dereferenced a null pointer, or whatever. And then there is signal 15, which is sig term, which is supposed to be like terminate nicely. So what the hell is the difference? So let's go into the signal handler example. So I am going to write a program that is a jerk and will have foiled you before this lecture. So I'm going to make a program that just ignores you typing Control-C. So, and this is a fun program to give to someone that hasn't taken this course. So I'm going to write my handle signal function. So like I said, it returns nothing and takes an integer argument with signal number. And I'm going to be a jerk where I'm just going to print out ignoring signal and then print out the signal number. So you'll probably only copy and paste this, so don't worry about it too much. But I'm going to register my signal handler. So it takes this struct sig action, has a whole bunch of math we're not going to worry about in this course. The only thing we really care about is that one of the fields of the struct is this signal, the sig action handler. So this is just the function that it's going to call whenever your process receives a signal that you register. And then you register an individual signal number through this sig action signal call. So you register the signal number to intercept, or actually run your action handler with, give it that new action, which will register that function, and then of course we error check. All right, aside from that, the program is going to be that cat example, where again, we just read and write bytes from, well, we read from standard in, write to standard out. So I'm just going to register sig int and sig term. So now if I run this program, what did I call it? I called it signal example. So anyone want to guess what happens when I press Control-C now? Yeah? Yeah, it just ignores it and taunts you, right? So I hit Control-C. Oh no, good thing I programmed defensively now. So I get ignoring signal 2, but I also get an error from my read system call. So so the signal handler happened. It ignored my signal, it printed it off, and then it returned wherever my program was at when it received the signal, which was in the middle of this read system call. And it made it, by default, return an error. That error was interrupted system call. So good thing I programmed defensively, otherwise my program would have just kind of ended and probably some weird things would have happened. So turns out this actually isn't a real error. All I would have to do is be like, oh, okay, well, if I got interrupted, I just restart and call read again. So I can write version 2 of my program that handles that. So how I would handle that is I'll check if I got an error, so bytes read is equal to -1. And then I'll check if that error no is equal to E, and you'll have to look this up, but interrupted system call corresponds to this error, E int R, and then I'll just continue, which means I'll just restart the read system call again. Otherwise, if I didn't get that, it's a real error. I want to break out of that and then print that error. So now if I run it and I hit Control C, just says ignoring and keeps on running, right? So we could hit Control D since we learned how to do that now. But if you gave this to, let's say, one of your other classmates before this class started, and they hit Control C and it just taunted you, how do I exit it now? Anyone know how to exit this, or are you all screwed? So I can just give you this and then you're stuck in it forever? This should be like a requirement to pass this course. You have to exit out of this program. Yeah?
Does Control Z still work if you kill with the PID?
So I don't need Control Z, Control Z, but you want me to kill it with the PID, right?
Yeah.
Oh, that's a way. OK, so there is, again, we're going to increase our vocabulary with kill, so now we can kill some children. So I don't know why they named this, but the system call to send a signal to a process is called kill. I assume because historically, the only thing you could do to a process, so one of the process numbers was seg kill. I assume originally they didn't have numbers and it was just sending kill to that process, which is why it's called kill instead of something nice like send signal. But who knows? So yeah, one of the suggestions was if I know the PID of this, I can try and kill it, which is like, please terminate. So to find the PID of that process, I can use PID of. So PID of, it's called signal example-2. So that gives me the process ID of that process, which is currently running and taunting me. So you said I should just kill it, right? So I could do kill, whoops, and then give it that number. So kill 5,000 whatever. So kill. So I sent it. It should be dead, right? So let's go back and see. Ignoring signal 15. So if I just kill, so everyone's used task manager and like tried to end task, right? What do you do if end task doesn't work? Restart the laptop. OK, that technically works, but without restarting the laptop. What do you do in Windows lands or any Windows or Mac users? What would you do? Or what does it complain at you to do? No one's had to choose violence before? Everyone's programs have worked properly? Really? Yeah. Yeah, like if you like go in Windows Task Manager, some process isn't responding, and then you go to end task, and then it doesn't end. We tried Control C, it doesn't work. Yeah. 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 Force quit, right? Force quit or end task or kill violently. So the Unix equivalent of that is that kill signal. So this kill by default will send a terminate signal to that process, which is 15, which is like, please terminate nicely. I would like you, and that gives you the opportunity to like clean up any resources or like finish doing whatever you're doing. But if a process is not behaving correctly, there is a violence option. So the signal, which is called kill, is the kernel will terminate your process. You have no say over it. You cannot handle that. And it is signal 9. So if I do kill -9, so kill by default sends signal 15. I can do dash and then a number to send any signal number I want to that process. So if I do kill -9 and then give it that process ID, now it is finally dead. So now it says terminated by single sig kill, forced quit, end task. This is like the forced quit. If you're using Windows or Mac and you press the forced quit button, essentially it's going to do the same thing, send a kill signal to it. and that is something you cannot handle. The kernel immediately terminates your process. It's not allowed to do anything else. It doesn't get to clean up or do anything fun. Whew, that was fun. We violently killed it. All right, so now we know how to exit any process. So any questions about that? Yeah?
What if you are not able to open like a new terminal?
If you're not able to open a new terminal, then that's bad. I don't know. You fork bombed yourself. You ran out of process IDs. You probably should have set your kernel to protect against that. So if you can't open a new terminal, then that's like in Windows. If you can't open Task Manager, then you can't open Task Manager. You're screwed. You got to reboot at that point, right? You're kind of over. All right. Other questions about that? So we now know the violence option, -9. So questions about that? Fun things? So anyone remember what a cool process is? That's really, really important. That's like the orphanage. Any cool processes? Yeah. The init process is one, right? Anything cool I could do? What about if I kill process 1 violently? All right, let's skip that. I was thinking out loud. Don't worry about it. All right, so quick wrap up before that would probably do something bad. So let's rewind a bit and go back to wait. So most operations or system calls are non-blocking that you do or that you hope to do. So non-blocking returns immediately, and then you check if something occurs. So we saw wait before. That was a blocking system call. Maybe you don't want to wait for one of your children to terminate. Maybe you just want to check if they have terminated or not. So I can use wait PID with W-NoHang. Basically, that will turn it into the non-blocking version. And to see whether or not a process has died, like with, I don't know, figuring out has something happened in hardware, I can either do pulling or interrupt. So let's go back here. Let's write a program. I can just fork immediately, and then in the child process, I'll sleep for 2 seconds, and then it will just terminate. So I can just write this here just to make it easier. So sleeps for 2 seconds and then terminates. And then in the parent, if I wanted to use the non-blocking version of wait, well, this one's going to be a bit silly because all I'm doing is waiting for my child. But if I wanted to do it, I could do it in a big while loop, right? So just because I'm curious, I can count how many times I call the non-blocking wait. So I'll just, if wait PID returns 0, that means my child process has not terminated yet, but there's no error or anything like that. So I'll just go through this loop while wait PID is equal to 0. Otherwise, it should return an error or give me the PID of the child that has now terminated. So I'll print off calling wait and then attempt whatever, and then call wait PID, give it what I got back from fork, which is the PID of my child, and then fill out wait status, give it that no hang option, and then after I break out of this loop, so I get finally a PID, which is either -1, an error, or greater than 0. Check if it's an error, print an error message. Otherwise, I assume that I just got the process ID of the child. I'll print off wait returned, print off that PID, and then that exit status of it. So this kind of looks familiar, but let's see the non-blocking or the pulling version. So wait pull example. So if I do this, turns out 2 seconds is a lot of time, and I do a lot of unnecessary work. So I pull it, you know, about 250,000 times at least. So that seems less than efficient. So if I wanted to reduce the number of wait PID system calls I make here, how do I more efficiently pull this thing? Any input how I would more efficiently pull this thing? Or remember the options in our hardware course. Yeah?
Maybe you can just wait between every core.
Yeah, I could just wait a little bit, right? So what about if I just do, I don't know, I wait. Let's just say I'll just sleep for a second. So I'll sleep for a second. Whoops. Oh, crap. All right, so I have to choose violence. Well, good thing I took this course, so now I can kill it. So compile, and then pull. So now if I do this, see attempt 1, attempt 2, attempt 3, so it took me 3 seconds. So more efficient here, but there's always a trade-off if I have to pull, right? So worst case, I have a bad response time. So worst case, I might pull, and then right after it says no, it hasn't terminated yet, and then immediately after that it terminates, but I sleep for a second. So worst case, I might only get notified it terminates up to a second later, which is pretty bad. Or if I want it to go lower, I have to reduce my sleep amount, which means I'll pull it again more times uselessly. So there's always that option for pulling, but if I don't want to pull, and instead maybe I want to clean up my child immediately when it exits, the other option to pulling is just interrupting. So remember when I told you before in the last lecture, the operating system will poke your process that, hey, your child has terminated, please clean it up, and by default you ignore it. Well, it turns out that poke is a signal. So when your child process dies, you get sent a signal with the signal number sigChild. The default signal handler just ignores it, but if you wanted to actually immediately clean it up without having a blocking system call on it, you can register a signal handler for sigChild, and in sigChild, just to be sure, you can just call the w-no-hang, and here, remember how wait by default returns whenever the first child terminates? Well, if I give wait PID the PID argument of -1, it will have that same behavior. So it will return for the first child has terminated, because in the signal handler, in this case, I don't actually know the PID of my child without making a global variable or something like that. So I'll just set it equal to -1. So I will just do a non-blocking wait PID in my signal handler. So whenever my child dies, I should immediately get sent a signal by the kernel. Then immediately I clean it up so I do not create any zombies or anything like that. And I am a non-neglectful parent. So I'm a good parent in this case. So I clean it up immediately when it's done. And in this case, since I'm not doing anything else, I'll just terminate that process. So just to show you it runs, so let's just do the wait. So, oh yeah, sorry. And just to show you that the main could be doing, or the original parent process could be doing something useful. Well, here the child sleeps for 2 seconds like before. And in the main process, I just put to sleep for an absurd amount of time. And that will block, the thing executing main to show you that the interrupt actually happens concurrently with whatever's running in main. So I just put main to sleep for a stupid amount of time. While it's sleeping, it gets sent a signal. And then after my child dies, after 2 seconds, then I clean it up, print off that, hey, we exit for a process, and then I just terminate my process because I'm not really doing anything more useful. But you could imagine that instead of that sleep 9,999, your program's actually doing something useful. So any questions about that? So that's our other option. You'll probably want this in lab 2 whenever it happens next week. Yeah?
What if we have multiple children? How do we, make sure we are only alive to terminate them all and not alive longer?
Yeah, so if I have multiple children, what I can do is I could call this wait multiple times. So if I call wait PID multiple times, eventually if I wait on all my children and they're all dead, it will eventually return an error of -1. And one of the error codes is no more children. So I can just constantly call wait until I know I have no more children. Or it returns 0, which means none of them has terminated. So there's kind of, yeah, I call it in a loop, and two conditions to terminate that loop. Either I have no more children anymore or nothing has terminated. All right, other questions before we can do some more fun things? Okay, well, as the last example too, yeah, some more fun things. Whoops. So, one thing you might want to do, which it kind of gets into threaded stuff, is like, hey, maybe I have this file descriptor open in my process, and whenever someone tries to terminate my process, I want to go ahead and be nice and clean it up. Maybe I'm buffering something. I want to write everything out before I terminate. So you might want to write this handle signal that is like, okay, well, before I exit, I'm going to close that file and then exit. So here I check if that file descriptor is valid. This will be set for main. So if it's -1, no open file, I just exit. Otherwise, I try to close that file descriptor, make sure that there's no error, and say I closed file. And in this case, I'll just simulate something else happen for 10 seconds, and then exit to exit the process. Now, in this case, I'm going to register a signal. Well, that's my register signal function. And in this function, I'll just write out my PID just to make it a bit easier so I don't have to do that PID thing. And then I'll open the file, say that I opened it, register sigint and sigterm, which is, Control C, and just that normal kill. And then just simulate I'm doing some work, sleep for 9,099 seconds. So if I run this, I get its process ID 6654, and it has, well, it actually hasn't opened a file yet. Sorry, I should give it a file. So, oh, that's a nice number. All right, 67,000 is that process ID, and it has opened a file. It got file descriptor 3 for that 0, or for this file. So we can imagine this program's running, it's using that file, it's writing to it, maybe it's reading from it, whatever, it's reading from that file. So let's set it up on the other terminal to kill. So maybe I say I'm done with this program, I hit Control C, and then it's trying to close that file, so it's closed that file, but maybe I get impatient and then I try to kill it. So if I look at it, well, what could happen is something very, very annoying, so that when I was in the middle of handling a signal, another signal came in, which would make it a recursive call, which is fun. So in this case, I actually got an error from close saying bad file descriptor, because it turns out I have already closed that file descriptor. So what happened in this case is, which is why signal handlers are kind of a pain in the butt, because they can happen recursively. So when I first hit Control C and set signal 2 to it, my process immediately started running this function. It printed off closing file and exiting, so signal 2, and it didn't get, like the file descriptor is equal to 3, so it didn't print this off. Then we closed file descriptor 3, it didn't have an error. It printed closed file, and then it was asleep for 10 seconds just to simulate, just to give me time to do it so that I can hit a recursive 1. So while it was in that middle of sleeping for 10 seconds, I sent signal 15 to it, which would essentially simulate calling handle signal again in the middle of this. So a new call would happen in the middle of it, where it would say closing file and exiting signal 15. Well, file descriptor, that global variable is still equal to 3, so this doesn't happen. And now close of file descriptor 3 gives me an error because I've already closed it. So this is bad, and you have to be very careful. So all your interrupt handler code must be something called reentrant. So while in the middle of executing it, it should be able to call itself again and nothing bad should be able to happen. So it should be able to pause execution in the middle of it, execute another call to itself, and then resume execution from wherever it went off, which is actually kind of a hard topic. Do not worry about it for now. This will get revisited once we start talking about threads. But this property is actually really, really hard to program for. And it's one of the reasons people don't really like signals at all. So with that cautionary tale out of the way, let's try something fun. So any questions before we wreck my computer? All right, well, let's see here. So like we said before, process 1, fairly important, right? If I try and kill 1, nothing will happen because it'll probably just ignore me. In fact, it says operation not permitted. Oh, probably because I'm not the root user, right? So I can just sudo kill 1. I'm now the root user. Enter my password. OK. Nothing happened. Probably because they made it ignore that, right? Because that doesn't really make sense. They probably shouldn't kill it. Well, if I wanted to actually kill it, again, what do? Kill -9, right? Like, I really want you to die. And nothing happens. So turns out kernel's smarter than us, and they actually ignore that. They don't let you kill process ID 1. But remember last lecture, there was some fairly important process. So when I ran that orphan example last lecture, remember my child got adopted by some special process, which was like systemd for my user. So it turns out the kernel doesn't protect that. So that is the process that's like acting as the orphanage for my user, basically spawning every process for my user. So this process ID 17,001, pretty important, right? So what would happen if I just did, kill -9, whatever that number, 1701. So any guesses what happens if I kill this violently? No guesses? Seems like a fairly important process that spawns every other process for my user, right? Including what I'm currently typing into, because VS Code is running as a process. My shell is running as a process. So let's just see what happens. All right, we're done.